Alright, so this video is going to look at some examples of trigonometric substitution. I'm also going to include some hyperbolic substitutions here. And just to give you a big picture, there are some problems where hyperbolic substitutions are easier than trig, and sometimes vice versa. So I think it serves you best to know about both. So let's get to it. So the first example, well, the big idea here is that a trig substitution is based on making an implicit substitution that involves a trigonometric function. So in this example, I make a substitution of theta. So if this were like, U substitution, as we discussed in first semester calculus, then we'd say u equals to something, right? But you notice here that the substitution is implicit in the sense that x is the old variable, theta is the new variable, and we're wrapping the new variable theta up in terms of some relation with the old variable, so x equals to sine theta. Now the reason to do that is that making this kind of substitution allows us to remove the radical. See, this integral right here, you're like, oh, wait a minute, I know that integral. That's a basic integral, the integral that's inverse sine. Well, very good. Congratulations. I'm glad that you know that. That's great. But I'm showing you a different way to derive that, all right? So this is just the one of the more easy examples to look at. We'll get to harder ones soon, don't worry. Anyway, so if x equals sine theta, when differentiating gives me dx is cosine theta d theta. 1 minus x squared is 1 minus sine squared, and see that 1 minus sine squared is cosine squared. That's the whole reason that we made this substitution, so that we can trade this sum of things under the square root for a square under the square root. And then, given the nature of the substitution, we know that the cosine theta would be positive, so that just reduces to just plain old cosine theta. So there we go. We have cosine theta d theta over cosine theta. The cosine thetas cancel, and that just leaves us integral d theta, which we can do. That gives us theta plus a constant. But remember, since x is equal to sine theta, we can solve for theta by taking the inverse sine. You may have seen arc sine before. That's just a different notation for this. And there you go. So inverse sine plus a constant, which of course is the basic integral. Perhaps you knew already that this is a basic integral of inverse sine plus a constant. So that's this technique I just used is called, again, trigonometric substitution, or just short for trig substitution. And again, this is not surprising since we know the derivative of inverse sine is 1 over the square root of 1 minus x squared. And so, this is a known elementary integral, but I've just showed you a different way to think about it. Now let's see how that different way of thinking allows us to do more interesting problems. Sounds like my coffee's ready. I don't know if you guys can hear that or not. Alright, so integral of the square root of 4 minus x squared. Well, that's something a little bit new, right? Now, again, we're going to make a trigonometric substitution to get rid of the square root. So what we do is we think about, well, what can I make x equal to that makes this sum, well, this difference of squares in this case, into a single square? And if you think about it for a bit, you realize that you could set x equals to 2 sine theta. So if I put x equals to 2 sine theta, that gives me dx is 2 cosine theta d theta. And so I've got 4 minus x squared is 4 minus 4 sine squared theta, but we can factor out the 4, right? Which gives me 4 times 1 minus cosine squared, 1 minus sine squared, which is 4 cosine squared. So this is what we get after making the trigonometric substitution, which is nice because now we've got 4 cosine squared theta d theta, which remember is a trig integral, which we've talked about in the previous lesson. And so we can just do half angle identity like so, and then integrate that. Now, this right here is not the final answer. We need to go back to x. And we like to leave our answer in terms of algebraic functions in as much as is possible. An algebraic function is a function whose formula is constructed with a finite sequence of algebraic steps. So this is the picture which indicates this substitution. the opposite. So if we solve this, it gives us sine theta is x over 2, right? So you can think about the hypotenuse being 2, the opposite side being x. By process of elimination, the adjacent side is the square root of 4 minus x squared. Or by the Pythagorean theorem, if you like, this squared plus that squared has to give me that squared. As far as any example I can ever think of, it's always the case when you draw this triangle that 2 of the sides of the triangle would be given by the substitution, and the remaining side will be the thing you're trying to get rid of. That's what should happen. Now, so one way we could write the answer would just be in terms of inverse sine. If we solve this for theta, we get theta as inverse sine of x over 2. So that's why I put inverse sine of x over 2, sine of 2 times inverse sine of x over 2. But of course we can do a little bit better with this. See, we could write that this is twice what? This is twice sine theta cosine theta, where sine theta is x over 2 and cosine theta is the square root of 4 minus x squared over 2. And so the 2's cancel, and we get 1/2 x times square root of 4 minus x squared plus a constant, and then of course this piece right here. Now this piece is not algebraic. That's a transcendental function. There's nothing I can really do about that. So there you go. That's an example, I would say our first non-trivial example of trigonometric substitution. Let's go on to example 3. By the way, towards the end of this video, I will make a summary of the different methods, and we'll try to make a kind of summary of what we're doing. So if you don't understand where the substitutions are coming from at the moment, be patient with me. We'll get to a kind of summary of this at some point. Of course, you could go look at your textbook even now. All right, so the answer star in the previous example 2, again, gives the result in terms of algebraic functions as much as is possible, since inverse sine of x over 2 is not an algebraic function. All right, let's move along here. So, example 3, we have the square root of x squared plus 4x plus 13. It is unfortunate that textbooks tend to underemphasize this problem. I can only assume it's because they believe that students can't complete the square. And that's unfortunate, because we definitely assume that students can complete the square. It's an important algebraic skill. If you don't know it already, you need to hone your skills. So to complete the square, what I do is I take half of the middle term, I add it to the first term, I square it. And then I just, well, personally, how I do it is I think through what that means then. I've got x plus 2 squared. All right, so x plus 2 quantity squared. Let me write it out down here, just to give you a little bit of internal logic here. X plus 2 squared, well, that's x plus 2 times x plus 2, right? Which is x squared plus 4x plus 4, right? Now, if you think about that, well, we've already got, right? What do we already have? We already have the x squared. We've already got the 4x and what's up here, right? This 4 is new. So if I add 4, in order to be fair, in order to make the inside of the square root, I guess that's the radicand, the input to the square root equal to the input to the square root, well, we still need another 9, because there's already a 4 if we multiply that out, right? 4 plus 9 is 13. And that's why I put the 9 here. So I just think through, if I multiply this out, how would I get back to there? Make sure it matches, and that's completing the square. Now you may have been taught some sort of algorithmic process for completing the square, but I would encourage you to think through it for yourself. All right, so the square root of, let's see here, we got x plus 2 squared plus 9. Now this is a different pattern. Now we've got the sum of squares. Before we had difference of squares in our previous 2 examples. For the sum of squares, a convenient substitution is sometimes made by tangent theta. So let's see here, we put x equals to x plus 2 equal, actually I'm about to show you that this is an inconvenient substitution for reasons that will become soon clear. So this is x plus 2, if I put x plus 2 equal to 3 tangent theta, then when I square that, that that puts it 9 tangent squared theta plus 9. I can factor out the 9. We know that tangent squared theta plus 1 is secant squared theta. So this gives me a square root of 9 secant squared theta. Dx, by the way, gives me 3 secant squared theta d theta, because we know the derivative of tangent is secant squared. By the way, I don't have to look that up. I just know that. I hope you know that. If you have to look that up, that's taking valuable time away from you. You should be focused on, integration, where you're going back and doing differentiation. You're already supposed to know. Just a comment. Anyway, so where are we? So the square root of 9 secant squared leaves me 3 secant squared, and the 3 times 3 is 9. We have integral of secant cubed. Oh, integral of secant cubed. This is not one I did in the previous the previous lessons. This requires me to actually stop and think a bit. I'll let me get a different sheet here. Excuse me. This can solve by integration by part switch loops. Here, I'll show you that. All right, here it is in all of its glory. So integral of secant cubed is the integral of secant theta times secant squared theta d theta. Now that's a dv uv minus integral of v du. Great. Now, all right, so the du, of course, was secant theta d theta, right? Excuse me, secant theta tangent theta d theta from du. So the secant theta, the tangent theta, doubles up with the v equals tangent theta. They can be tangent squared. Then trade out my tangent squared for my secant squared theta minus 1. That leads me back to a minus integral of secant cubed minus the integral of secant theta d theta. So we got integral of secant theta, secant theta tangent theta plus the integral of secant minus the integral of secant cubed. Wait a minute, that's what I was trying to find, except I got back minus what I was trying to find. So if I add integral of secant cubed theta to both sides, then I've isolated the integral. And so that gives me that the integral of secant cubed theta d theta is 1/2 secant theta tangent theta plus 1/2 the natural log of the absolute value of the sum of secant theta plus tangent theta, because that's what the integral of secant theta is. I guess I haven't worked that out this yet, but we'll get back to that, I think. Or I'll add it in somewhere here. And there you go, that's the integral of secant cubed theta. That's kind of a tough one, isn't it? So continuing from star, which if you've forgotten is up here, this was star. So continuing from there, in view of the integral we just found, we get, let's see, try to get everything in the picture. The integral of that square root is, we get the 9 from the star again. That 9 is not from here, it's from the star. 9/2, secant tangent, plus 9/2 natural log of the sum of secant and tangent plus a constant. Great. Now, then there's a, here, let me just go all the way down here so we can see what we're doing. So to explain this, this is the triangle which pictures the substitution. The substitution was tangent theta is x plus 2 over 3. So that means that hypotenuse over adjacent side, which is, by the way, secant, is 3 over x plus 2. Excuse me. Other way around. It's the, I'll get with it eventually here. Oh, excuse me, that's x plus 2, that's 3. So the secant theta would be, what would it be? It would be 1 over cosine. That would be hypotenuse over adjacent side. So that would be secant theta. Tangent theta, of course, is x plus 2 over 3. So putting those in, secant theta is that, right? Tangent theta is x plus 2 over 3. This 3, and that 9 cancel. And again over here we get this, all right? And so there you go. There's the answer as best as I can in terms of algebraic functions. Actually, I can simplify this a little bit. I think I'll do that on the next page. We'll see. So continuing from star star, which was the last thing we got to, we can simplify this to actually natural log of 1/3 absolute value, but absolute value bars here aren't really needed. And then natural log of the absolute value of x plus 2 plus the square root. All right. So this is by properties of logarithms. So I can actually absorb this constant into my constant for the integral, and simplify my answer just a little bit like that. There you go. It's important to know this sort of thing if you're looking up, answers in the back of a textbook. Sometimes textbook will make these kind of simplifications. And if you don't know about it, if you don't know properties of logarithm, it could make it seem like your answer is wrong even when it's right, right? All right. If you're ever in doubt about whether your integral is right or not, you should just differentiate it. If you can differentiate it and you get back to the integrand, well, you integrated right? Okay. Now, this example is similar to example 3, but this time I'm going to use a hyperbolic substitution because as much as I enjoyed showing you guys integral of secant cubed, it'd be nice if we could find a simpler way. So if this problem actually came up on a test or something, I would encourage you to use the technique of example 4. Let's see how it goes. Integral of x squared plus 16 square rooted is, well, if we make it x equals 4 hyperbolic sine substitution, dx is 4 cos theta d theta. X squared plus 16 is 16 sinh squared theta plus 16, which simplifies to 16 cos squared theta. Ooh, very nice. And again, just a reminder, that's because cos squared minus sinh squared is 1, which means that cos squared is 1 plus sinh squared. So this simplifies to, sorry, I'm an idiot. 16 cos squared theta d theta. Now cos squared has very similar, similar fun facts to cosine squared. In particular, one of those is that this is 1/2 of 1 plus cos 2 theta. Hey, maybe that's one of those sorts of things that belongs on your sheet of memory. This is you do, after all, have an open book test in our current format, and so yeah. Of course, who knows, maybe at some future date we'll have closed book tests, so keep that in mind as you watch this, that I'm speaking of the era of open book tests. Anyway, I can, of course, imagine a world where we had closed book tests. Anyway, I digress. So here we go. 1 plus cos 2 theta integrates to, of course, theta plus 1/2 sinh theta, sinh of 2 theta. And then we just have to put back in what theta is. Now, of course, since x is equal to 4 sinh theta, that means that x divided by 4 is equal to hyperbolic sine of theta, sinh theta that is. And then you just take the inverse hyperbolic sine of both sides to get theta inverse sinh of x over 4. And 8 times 1/2 is 4, so 4 sinh of twice inverse hyperbolic sine of x over 4. Let's see here. That can be simplified. I'm not sure if I did or not. Oh, we could also do example 3. So in retrospect, right, this was easier than integrating secant cubed, right? And if you think about it, we could have done example 3 using a hyperbolic substitution, right? We could have used x plus 2 equals 3 sinh theta, and that would have made it more like this, all right? And we could also take this answer and we can rewrite it in terms of natural logs, all right? And so, like, what I'm trying to say is, if we look at, just to give you thoughts on my brain, so this was where was our ultimate answer? Oh, it was on the same page, I'm an idiot. All right, so this was our answer from part 3. It's got algebraic function, then 9/2 natural log of this stuff, right? In contrast, the example to number 4 was inverse hyperbolic sine, right, in this. And you might wonder how those two answers could actually be kind of the same sort of answer. The answer lies in the fact that inverse hyperbolic sine can be rewritten as the natural log of an appropriate algebraic function. So if you use this relation between inverse sine and natural log, you can actually see that answers like this and answers like that are the same form, actually. These are not the same answer, these are different problems, all right? But anyway, this inverse hyperbolic sine is natural log of that is one of those things that's at times nice to know about. If you find yourself needing this, you're asking something that's a little bit picky, but that's good because we are picky. All right. I mean, you're learning calculus, second semester calculus. There's not a lot of people in the world that know this in the sphere, at least the American world. The part of the population that could actually do second semester calculus competently is relatively small. You're trying to enter that segment, and which qualifies you for a certain subset of degrees and so forth that other people might not be able to do, which means you have a certain technical expertise, which is a challenge worth attaining. And setting aside that degree-seeking kind of nonsense, I think it's just fun. All right, so we got x equals to 7 secant theta. X squared minus 7 is going to be 7 secant squared theta minus 7, but we can factor the 7 out, which gives us 7 tangent squared theta. I've moved on to example 5 if you hadn't noticed. And then dx is square root of 7 secant theta tangent theta d theta. Let's see here. So when we make the substitutions, we get a cancellation of our tangent theta and also the square root of 7, which leaves us square root of 7 secant squared theta. Well, that's a welcome sight. Integral secant squared is just tangent theta. Yeah, that's not bad. And then we can leave our answer as an algebraic function because, remember, there's the substitution triangle, if you will, is x over the square root of 7 is equal to secant theta, which says I can make x the hypotenuse adjacent side, square root of 7. And the remaining opposite side has got to be the thing we were removing, which is square root of x squared minus 7. And so tangent theta is opposite over adjacent, which is that over that. The square root of 7's cancel, and there's my answer. Now, this problem in here, there is an easier way to do this problem, right? What's another way we could solve problem 5? We could simply make a u equals x squared minus 7 substitution, which would immediately give us integral of 1/2 du over the square root of u, which is just integrating to the square root of u, plus a constant, which would have been that. So u substitution would have been a smarter way to do this, right? So trigonometric substitution, at times, and this is a very special case in the sense that there's an easier way to do this one. So why do I include this? Well, because it's another good example of trigonometric substitution. But you gotta, when you integrate with both eyes open. Remember that you have a variety of techniques, and which one works best is the best one to use. Which one is the one that's best? Well, probably the one which you're most comfortable with. Of course, if instructions have been given, if I say use integration by parts to do something, then you better use integration by parts, right? If I say give your answer as an algebraic function, then you probably better do that. If I say give your answer in as much as possible as an algebraic function, well, you probably better convert as much of it to an algebraic function as you can. And I've been doing that in our answers so far. So let's move on to example 6 here. And just another generic comment, I've been writing out things with proper notation, which means that I've been indicating equality between where there's equality. My expressions aren't just floating around. A lot of times students have a tendency to just kind of like machine gun equations all over the place, and they don't really organize their thinking. Organizing your thinking is important to us, and you need to try to convince me or your instructor that you know what you're doing. And so one way you can do that is to express your mathematical thoughts in a way which is similar to what is customary. And I'm showing you what's customary in these videos. All right. So here we go. Integral of dx over x squared plus 1 squared. Oh my goodness, x squared plus 1 squared. Now that we have not seen before. And this is a definite integral. So here we're going to get a chance to see how trigonometric substitution works with bounds. And whenever we make a substitution, we have to change the bounds. All right? And so that means I go from x bounds to theta bounds. If I make an x equals tangent substitution, as is a good one here, then my dx is secant squared theta d theta. Now if x is equal to 0, that means 0 is tangent theta. That suggests to me I can make theta equals to 0. If x is equal to 1, tangent of what is 1? Well, tangent of 45 degrees, or tangent of pi over 4, I should say, is 1. So that changes my 0 to 0, well, not much of a change there, right? But changes my 1 to pi over 4. The denominator is secant squared squared, which is secant to the 4th. And we get 1 over secant squared theta, which of course is just cosine squared. And then back to our half angle identity. Here it is again. Integrate. Now we integrate both those pieces. It gives us a theta. This pulls out a 1/2 from the cosine 2 theta, and that simple substitution of the 2 theta. Excuse me. And of course we have to do fundamental theorem of calculus, have to evaluate at the upper and lower bounds and take the difference as appropriate. So we get pi over 4 plus 1/2 sine of pi over 2 minus 0, minus 1/2 sine of 0. Of course this is all 0. So only pi over 4 contributes non-trivially to the answer, which is pi over 8 plus 1/4. There you go, our first trigonometric substitution with bounds. Alright, pretty much the same song and dance, just got to follow the, change the bounds. Alright, another example. Example 7. If we have dx over x squared times the square root of x squared plus 4, by the way, my internal logic is, hey, can I do a u substitution here? I think for a second go, oh no, I can't. So probably trigonometric substitution is a good choice because it's got a square root in it. Or possibly hyperbolic, let's see what happens. So dx is secant squared theta d theta, and if I make x equals 2 tangent, I do that because I got a sum of squares down here, so tangent's a good substitution. I put a 2 to match the 4 after I square it, yeah. So x squared plus 4 with this substitution is 4 secant squared theta, which gives me dx is 2 secant squared theta d theta. Alright, like so. The some of that cancels, right? We're left with just a secant over tangent squared. And I look at that and go, and then I say, well, I'd rather look at that in terms of sine and cosine. Then I can kind of know what to do. I go back to, fall back on some of those trigonometric integrals we did in a previous lesson. Alright, so I've got an odd total number of sines and cosines. I had to be able to keep one of these sines or cosines for like a u substitution. Yeah. So I tilt my head and squint, and I say, oh, I got cosine theta d theta over 4 sine squared theta. That means I'm going to make a u equal sine substitution, my du, cosine theta d theta. So this is du over 4u squared, yay, which is integrating to minus 1 over 4u, which, going back to sine theta, is minus 1 over 4 sine theta. Remember that my tangent theta is x over 2, right? Which gives me this triangle to picture the substitution, and the side which is missing is the square root of x squared plus 4 by the Pythagorean identity. So sine theta would be x over the hypotenuse, like so, and then algebra. Simplify. The denominator serves as the numerator in this context, so that's minus the square root of x squared plus 4 over 4x plus a constant, and there you go, the answer in terms of algebraic functions. Answer in terms of algebraic functions in as much as is possible. Alright, so finally then, I think we have earned the right to make a summary of what we're doing. And here's the key, here's the big picture. I would encourage you to put this on our sheet of remembrance, let us call it. The key identities for what we're doing is that sine squared plus cosine squared is 1, and that cos squared minus sin squared is 1. And also that, of course, gives me these identities for tangent and hyperbolic tangent. We haven't even seen that in play in my examples here. And the thing is, we can tame a square root of this kind, that kind, or that kind by these substitutions, either secant theta, sine theta, or tangent theta for the trig substitution, or the corresponding hyperbolic substitution would be cosh, tanh, or sinh. I've showed you a sinh substitution, and so the distinction between the 6 substitutions and u substitution is again in the structure of the substitution. Contrast u equals stuff to x equals a secant theta, x equals to a sine theta, x equals to a tangent theta. The theta is new, or in the hyperbolic substitutions, the beta is new in my current language. So I think a better term for trigonometric substitution would be implicit trig substitution. Anyway, words aside, you should recognize this technique successfully removes the square root by introducing squares in place of the sum or difference given in the squared quantities. As usual, you won't be surprised to hear me tell you that the key to mastering this technique is practice. So, anyway, thanks, and that concludes this video.